Welcome to this state-of-the-art report on computational design of assemblies with rigid parts. My name is Mark Pauli. I'm a professor of computer science at EPFL, and together with Ziqi Wang, who's a PhD student in my lab, and Pang Song, who's an assistant professor at the Singapore University of Technology and Design, we will present an overview and a survey of algorithms for computational design of assemblies. Here is a rough timetable. I will start with an introduction and then hand over to Pong, who will look at computational analysis methods. And he will be followed by Ziqi, who will talk about design algorithms. And then we'll have some time for discussion and future work, and of course also for questions and answers. So let me get started on the introduction. 3D assemblies are really ubiquitous in our life. Here you see examples of toys, furniture, a watch, a car, many structures and architecture. And these assemblies are composed of multiple parts and have a very specific form and functionality. So in this state-of-the-art report, we'll look at assembled objects, not monolithic objects like you see the one on the left, which is carved out of a single block of material. And these type of assemblies come with a number of advantages. First and foremost, fabrication. We can simply fabricate geometrically much simpler parts that can then be assembled into a compound object, which can have a much more complicated shape and also interesting functionalities. This allows us further to store and transport the component parts in a compact way. Finally, we can very easily maintain an assembled structure. For example, if we have to replace a broken part, they allow for multiple forms. They can be reconfigured in various ways, which incidentally also allows multiple functionalities. Assemblies are also, of course, used in dynamic settings, for example, here to transfer motions. So, in summary, the advantages of these type of 3D assemblies come from the fact that we can take simple forms and aggregate them into complex shapes. They can be disassembled and rearranged, for example, for storage and transport, and we can reassemble and reconfigure assemblies to adapt their form or functionality. However, these advantages also come with various challenges for design. So let me quickly walk you through these design challenges. First of all, we have to look at how we can adapt the component parts to a specific fabrication technology. So there will be constraints on the fabrication imposed by a specific machine. For example, if we use laser cutting, we're constrained to a specific type of 2D materials. CNC machining comes with its own constraint, and 3D printing as well. Related to that, there will be constraints on material and appearance of the individual parts. We also need to figure out how we're actually going to join and aggregate component parts together. So what type of joining model are we using? How are joints interacting with the individual pieces in order to achieve the desired functionality? We also need to look at the assembly process. In many instances, we care mostly about the final state of the assembly, but we will also have to find a way to put the pieces together such that we actually achieve the final desired assembly. If we care about storage and transport, we need to find ways to aggregate and pack the individual parts. Very important, we want to, of course, during our design, create assemblies that are structurally stable. And we will look into this in great detail and see what that means specifically for the design process. In case of reconfigurability, like you see in these examples here, you add additional design challenges because the parts will not only aggregated in a single way, but potentially in multiple ways, which then relates also closely, of course, to the function of the assembly. And finally, you might have functional requirements, for example, load-bearing capacity that you need to take into account carefully within the design process. So if we want to look at a global view of the computational process for designing assemblies, the general idea is to come up with an efficient and effective way to come from an initial idea about an assembly to a final physical model. And because there are many steps involved, including designing the parts, fabricating them, looking at their structural and functional performance, computation is really a key to make this process effective. So in this report, we will look at the computational design process, and in particular, talk about various tools and algorithms that allow us to understand performative aspects of 3D assemblies. If we break it down schematically, we can see here the sort of pipeline from user input to the final desired output, and we will specifically look at these tasks of computational analysis, for example, to analyze whether a given assembly is structurally stable, and computational design, in particular, to define the shape and joining of individual component parts. So these two aspects relate to the main part of this tutorial. So in the first part, or I should say the second part after this introduction, we will look at tools to analyze computationally various assemblies. And then in part 3, Sichi will talk about algorithms and data structures to design for assemblies. The objective of this state-of-the-art report are to provide a comprehensive review of existing literature. We will cover a large number of different papers with a focus on the various representations, methods, and algorithms for the analysis and the design of complex assemblies. We'll specifically try to create links between these different works. So we try to categorize them, find similarities, find differences, so that you can create a more global view of this research. And in that sense, this STAR report is also aimed specifically at researchers that are new in this field, that want to get an overview and understand, the various different methods that are available. And finally, we use this categorization also as a way to identify maybe gaps in the research and present a few open problems and future research directions, because there's plenty of topics and problems that are unsolved as of yet. To define the scope a little bit further, we will look at assemblies that are composed of rigid parts. So we will not study assemblies where the deformation of the parts plays an essential role in the way the parts are connected, for example, like you see here on the right. Our focus will be on component parts that can be abstracted as rigid bodies. And this allows us really to focus on geometric methods and come up with efficient optimization problems that can abstract away many of the physical properties of soft parts. And finally, we will focus on structures as opposed to mechanisms. So as you see here in this video on the right, a core aspect of the functionality of this assembly is the kinematics, the motion that is generated by the assembly. Our focus will be on assemblies that provide, that can be considered as static structures. More specifically, if you want to distinguish between the two, in our focus on structures, we're looking at the interaction of the pieces in terms of force transfer, but not motion transfer. Typical applications, as I mentioned earlier, furniture pieces, architecture, puzzles, and so on. This distinction also has implications on the typical shape and function of parts, and changes the focus of design as well. And with this, I want to hand over to Pong, who will now look at computational methods for the analysis of assembly.
This is Pong Song from SUTT. I'm going to present the second part, computational analysis of assemblies. This part will take around 20 minutes. In this part, we introduce computational methods to analyze 4 different aspects of assemblies: parts joining, how to join parts together; assembly planning, how to assemble a set of parts into the final assembly; structural stability, what is the performance of the assembly under external forces; packing efficiency, how to pack the parts as tight as possible. Let's start with parts joining. It is common knowledge that parts in an assembly need to be joined together to make the parts stable. Compare these two house assemblies. The Lego house on the right is more stable than the wooden house on the left on the external forces. But why? It is because they use different parts joining methods. In the wooden house, parts are simply connected by the planar contacts, while parts in the Lego house are connected by the frictional joints. We call this geometry or material used to connect parts joints. Joints can be broadly classified as permanent and non-permanent. Typical permanent joints include adhesive materials such as glue and permanent mechanical fasteners such as riveting. Typical non-permanent joints include screws and woodworking joints. Compared with permanent joints, a significant advantage of non-permanent joints is to encourage parts disassembly and reassembly. Non-permanent joints can be further classified as external and integral. Screws and 3D printable connects are external joints, and they are independent from the parts. Woodworking joints and curved contact joints are integral joints. Integral joints can significantly simplify the assembly process by assisting parts alignment and reducing the total number of assembly steps. External joints can be further classified as conventional joints such as screws and customized joints such as 3D printable connectors. Integral joints can be further classified as woodworking, curved contact, and planar contact joints. An assembly can be represented by a parts graph. In a parts graph, each node represents a part, and each edge represents a joint between two associated parts, such as joint J1 between part P1 and P2. The dual of a parts graph is a joints graph. In a joints graph, each node is a joint, and each edge represents a part that is common to the two joints. For example, the part common to J1 and J2 is the green part, which is P1. Given joint geometry, we also can analyze its ability to connect two parts. Taking these four joints as an example, we can see that the joint's ability to connect parts becomes stronger from left to right. So how can we quantify the joint's ability to connect parts? Given a joint, its ability to connect parts can be quantified by its ability to restrict a part relative moment. In these four joints, if we consider only translational motion to take out the green part, all possible translational direction for each joint is visualized here. For the planar part, for the planar contact, the green part can translate along any direction in a half circle, while for the tendon joint, the green part can only move upward. So based on this motion space, we can quantify the joint's ability to connect parts. Now the question is, how can we compute this motion space, especially when we consider rigid motion? To answer this question, let's start with the simplest case, which is the planar contact. We assume the cyan part is fixed and calculate the rigid motion space of the green one. During the movement of the green part, the constraint is to avoid collision with the cyan part. So this collision-free constraint at a contact point C can be formulated by this equation, where Vc is the speed of point C and n is the normal of the contact. The constraint for a planar contact can be formulated by these two inequalities for two endpoints respectively. This is because we consider infinitesimal motion for the green part. When a joint has multiple planar contacts, we can formulate the constraint for each planar contact, such as C1 and C2, and then we stack all these constraints to form a system of linear inequalities. For curved contacts, we can use a sampling approach to compute its allowed motion space. In detail, we sample a number of points on the curved contact, list constraint for each contact point, and stack all these constraints to form a system of linear inequalities. Due to the sampling strategy, our computed motion space is an upper bound of the actual motion space. Now let's move to the second aspect, assembly planning. Assembly planning is the process of creating detailed instructions to combine separate parts into the final structure. Assembly planning is widely used in automated manufacturing, robotics, and architecture. Assembly planning will output 3 sets of information for assembly. First, the order to assemble the parts, also called assembly sequencing. In this example, the order is that we first assemble the orange part, followed by the blue, yellow, cyan, and the green one. Second, motion to bring each part to its target pose, also called assembly path planning. In this example, for the blue, yellow, and cyan parts, we simply translate them from left to right. And for the green part, we translate it downward. Third, utilization of additional resources for the assembly process, such as supports and tools. Look at this intermediate assembly. The blue part is held by using a support. Similarly, we use a support to hold the yellow part in this intermediate assembly. Disassembly planning is a reverse process of assembly planning. A bijection exists between assembly and disassembly sequences and paths if we consider only geometric constraints. This enables an important strategy for assembly planning, called assembly by disassembly. The advantage of this strategy is to dramatically reduce the size of the solution space for searching the valid assembly planes. This is because parts in an assembled state have far more precedence and motion constraints than the disassembled state. Classification of disassembly planes. Disassembly planes can be classified as sequential and non-sequential. A sequential plane is also called a two-handed plane. That means you can always use 2 hands to disassemble the parts. See this top example. The bottom example shows a long sequential plane or a 3-handed plane. We need 3 hands to disassemble it. 1 hand to fix the orange part, 1 hand moves the green one, and 1 hand moves the cyan one. An assembly is monotone if no intermediate placement operations are needed for the assembly. See this top example. The bottom example shows a long monotone plane. This is because in this first step, we need to move the green part to the right in order to take out the cyan part. An assembly plane is linear if all assembly operations involve removing of a single part from the rest of the assembly. See this top example. The bottom example shows a long linear plane. This is because the first disassembly operation involving removing 2 parts at the same time. A coherent plane means that each part that is removed will touch the rest of the assembly. See this top example. The bottom example shows a long coherent plane. This is because when we remove the orange part, it does not touch any part in the rest of the assembly. Disassembly planning is an NP-complete problem. To simplify the problem, people focus on the simplest disassembly planes, which are sequential, monotone, and coherent. Another reason to choose these disassembly planes is that they are easy to be executed in practice either by humans or robots. Now the question is, how can we find such a disassembly plane? One common approach is based on the path graph. We first compute mobility for paths in assembly using the method that have been introduced earlier, and to identify movable paths quickly, we usually select paths with fewer labels in the path graph. In this example, we identify and choose the green part. Next, we remove the green part from assembly and update the path graph accordingly. Then we repeat step 1 and 2 for the remaining assembly. For example, we identify and remove the cyan part, the yellow part, the blue part, until there is only one part left in assembly. One limitation of this path graph-based method is that it supports only linear disassembly planes. Look at the computed disassembly plane here. In this plane, we take out each single part at a time. Due to this limitation, this method cannot search a valid plane for this assembly since there is no single part removable from the assembly. However, there is indeed a nonlinear disassembly plane. In this plane, we translate the green and cyan part together along the same direction to take them out. After that, the yellow part can be easily taken out. To find this nonlinear disassembly plane, we need to test mobility for all possible combinations of the parts, which has an exponential complexity. So now the question is, how can we find this nonlinear disassembly plane more efficiently? One solution is to use the directional blocking graphs developed by Wilson in 1992. Given an assembly A and a blocking direction D, which is positive x here, nodes in the directional blocking graph represent paths in assembly, and we create a direct edge from Pi to Pj if and only if Pj prevents any translational motion of Pi along D. For example, here we create a direct edge from P1 to P2 since P2 prevents the motion of P1 along positive x. We can prove that if the graph is strongly connected, no part or part group is movable around D. Thus, the graph on the left is strongly connected. For example, the graph on the left is strongly connected, hence there is no part or part group is movable along positive x. A sub-assembly S of A is locally free to translate in direction D or minus D if and only if it is strongly connected component. Look at this sub-assembly. It is strongly connected component and it can translate along positive y. Note that finding strongly connected components can be done in big O n to the power 2, where n is the number of parts. Based on directional blocking graphs, we can find a nonlinear disassembly plane efficiently. First, we find one strongly connected components in the DBGs. For example, P1, P2 in this graph. Next, we remove the sub-assembly and update the DBGs. Then we repeat the first step and choose P3 in this graph. And remove the part P3 and update the DBGs. Since there is only one part left in the assembly, we are done with this disassembly plane search. By this, we find a nonlinear disassembly plane as shown here. Now, we will talk about structural stability. An assembly with rigid parts is structurally stable if it can preserve its form under external forces without collapse. Given these two assemblies, we know that the Lego house with friction joints should be more stable. But how can we quantify stability computationally? A structurally stable assembly means it can be in equilibrium under certain external forces. Taking this assembly as an example, it is in equilibrium under gravity. However, a lateral force such as those from the wind can easily make the collapse. In practice, an assembly should be in equilibrium not only under gravity but also under lateral forces. Tilt analysis is a process to quantify this lateral stability. In an extreme state, an assembly can be in equilibrium under arbitrary external forces. We call this structure stability state interlocking. Comparing these three states, we can see that the assembly becomes more and more structurally stable. But the cost is that the path geometry becomes more and more complex, since more restrictive joints are needed to connect the parts. The state-of-the-art static analysis method is a rigid block equilibrium method. Given the geometry of a 3D assembly, a static equilibrium state means that there exists a network of interaction forces between the parts that can balance the external forces acting on each part. Hence, the internal force on each contact plane is discretized as forces on the plane corners. Combined equilibrium constraints for each part give a linear system of equations as shown here. Besides this, we also need to formulate the compression and friction constraints. Please refer to the paper for details. Tilt analysis is the method to measure stability of masonry structures under lateral acceleration. In real experiments, the ground plane of a structure is rotated around a fixed axis to apply both horizontal and vertical acceleration to a structure based on the gravity. The critical tilt angle phi is used as a measure of the structure's lateral stability. One generalizes this measure by considering all possible rotation axes to tilt the ground plane. This stability measure is defined as the minimum critical tilt angle among all possible tilt directions. Interlocking test. We know that an assembly is interlocking if it is in equilibrium under arbitrary external forces. Here we define interlocking based on the statics. However, trying all possible external forces is infeasible in practice. Based on the static-kinematic duality, we can define interlocking based on kinematics. An assembly is interlocking if there is no movable part or subassembly except the key. Recall that directional blocking graphs can be used to identify movable subassemblies efficiently. Hence, we can make a connection between interlocking assemblies and the directional blocking graphs. Based on this connection, we can test interlocking much more efficiently. We show that if all these directed graphs are strongly connected except key, the corresponding 3D assembly is global interlocking. Thus, we can test the interlocking in the graph domain rather than in the geometry domain with polynomial time complexity. The limitation of the DBG-based method is that DBGs do not consider non-sequential disassembly planes. Taking this as an example, this method considers it as a dialocking. However, the green and cyan parts actually can be taken out by moving along different directions simultaneously. To solve this issue, one proposed a more general method to test global interlocking based on solving a system of linear inequalities. Consider an assembly as a rigid body system where each part can move in the 3D space. The constraint is a avoid collision among the parts. By staking the long penetration constraints for each contact in the assembly, we obtain a system of linear inequalities. The assembly is global interlocking if the system does not have any non-zero solution. According to this method, this assembly is not interlocking since the system has this non-zero solution. Okay, now let's talk about the last aspect of assemblies, packing efficiency. The goal of packing is to place as many objects as possible in a given container without overlapping. Extensive efforts have been devoted to packing irregular objects into 2D and 3D containers. The packing problem is known to be NP-hard. The goal of assembly packing is to pack component parts of a given assembly within a container. Since parts usually have irregular shapes, assembly packing falls in the irregular packing problems. Assembly packing is useful not just in saving storage and transportation space, but also in improving manufacturing efficiency and minimizing waste of fabrication material. The objective of assembly packing is to maximize the packing efficiency, described by this formula, and there are three hard constraints for assembly packing: the bounding constraint, the overlap-free constraint, and the assemblability constraint. There are two classes of approach to solve the assembly packing problem: iterative approach that places the given set of parts one by one in the container while minimizing the bonding volume. Global packing approach seeks to find assembly component parts in a packing configuration by solving a global optimization problem. Please refer to the papers for details. Summary and discussion. In this part, we have introduced computational method to analyze 4 aspects of assemblies, including path joining, assembly planning, structure stability, and packing efficiency. Future research efforts can be devoted to study more aspects of assemblies for computational analysis. such as tolerance analysis and functionality analysis. Okay, that's all for my presentation. The next part will be presented by Ziki Wang. Thank you for your attention.
Hi everyone, my name is Ziki Wang from EPFL. In the next half hour, I will present the recent works on computational design of assemblies. Then I will summarize and discuss these recent works and propose some potential topics for future work. My first research topic is about the assembly-based fabrication. The major reason for making assemblies instead of single piece is that every fabrication technique has its own restriction in terms of the fabricable shape. If the input shape is too complex or too large to be made, the assembly-based fabrication can address these problems by approximating the input's 3D shape with a set of simpler parts that satisfy the fabrication constraints. Here are 3 typical digital fabrication techniques. The 3D printing can fabricate almost any 3D shape, while the 2D laser cutting is limited by only cutting 2D shape. We divide assembly-based fabrication into 4 parts. In addition to 3 typical fabrication techniques, the mixed fabrication is an approach to combine multiple fabrication tools into one project. Let's first review the recent works in 3D printing. Material deposition and their solidification are 2 ways to implement 3D printing. Most domestic printers use the material deposition due to its simple machinery. However, this machine requires printing spot for all handling area. The layer solidification machine at the right does not need to print spot, but with a cost of higher price. Most of the research works in graphics still focus on the material deposition machine due to its high accessibility. For assembly-based 3D printing, our goal is to design an assembly which has less spot material, higher packing efficiency, and less appearance damaging compared with printing in one piece. The core methodology is the shape decomposition, which split input shape into printable parts with simple shape and then assembles the parts to obtain the target assembly. Let's first see how to reduce the spot material by using shape decomposition. Spot material, though can be printed in a low filling rate, still slows down the printing process, causes excessive printing material, and damages the smoothness of the printed surface. When the surface inclination angle alpha is smaller than a critical inclination angle alpha c, 3D printing material can be accumulated without extra spot structures because of the strong adhesion between successive layers. In extreme, when the inclination angle is 0 or below, we call the shape pyramidal, which is spot-free for any 3D printer. Therefore, our goal is to decomposite the input shape into spot-free parts to save spot material. The top-down and bottom-up are 2 classes of approaches for spot-free decomposition problem. Top-down approaches try to find a set of 3D planes that clip the input shape into a set of parts, aiming to minimizing the total spot. These 3D planes are organized as a binary space partitioning tree or BSP tree, see left. Yu and their colleagues proposed an evolutionary approach to search for these clipping planes, and their algorithm can save most of the spot material, see left. The bottom-up approaches, like the pyramidal decomposition paper, progressively build larger and larger interior elements of the input shape, from sample points to cells, blocks, and candidate pyramidal parts. The final decomposition, which is the selection of the candidate pyramidal parts, is obtained by solving the exact cover problem. Here is an output from their paper. The second objective is about packing. Decomposing oversized input design and packing its parts into a compact form saves storage space and reduces printing time and material cost. The sequential and the decomposite and pack approach are 2 ways to solve the shape decomposition for packing problem. Sequential approaches try to do shape decomposition followed by parts packing, while heuristics could be applied at the decomposition stage to encourage generating parts that are easy to pack. The decomposite and pack approaches optimizing shape decomposition and packing simultaneously. Yao and their colleagues take a set of pre-segmented parts as input. The framework represents each part as a level set function and optimizes the partitioning and packing to improve packing efficiency, as well as other metrics such as aesthetics. The third objective is about appearance. The assembly's appearance usually is affected by at least 4 factors: cutting seams, removing of spots, staircase effect, and material color assignment. The spot issue is already being discussed in the previous slides, so I will focus on the rest 3 factors. The first appearance problem is the cutting seams. Cutting seams are visible gaps between parts in the final assembly, which cannot be completely avoided due to manufacturing tolerances. To measure severity of the cutting seams, one approach is based on the ambient occlusion. See left. The cutting seams should avoid high obtrusive area. And another approach is to make cutting seams aligned with surface details by using non-planar cuts. See right. The second appearance problem is the staircase effect, which can be seen from the left Armadillo model. The reason for having staircase effect is that the input shape is smooth, but the printer can only print staircase-like shape. See left figure. Therefore, 2 typical ways are designed to measure this effect. One is the cusp height, see H in the second figure. Another is the volume difference, see the right area in the third figure. To fabricate an input model whose outer surface consists of regions with different attributes as a single piece requires using multi-material printers, which are too expensive for domestic environments. Therefore, recent works want to decomposite the input into parts and print parts into different material and color to obtain an equivalent result. Like the left furniture with a decorated joint, the key element here is to avoid deadlocking while maintaining structure stability. Here ends the 3D printing, and we move to the problem in CNC milling. CNC milling is the process which subtracts material from a starting block. The machine is less constrained by the material and enjoying a higher manufacturing position compared with 3D printing. According to how many degrees of freedom the milling bit has, we have 3-axis, 5-axis, or even 5+axis machine. 3-axis CNC machine is the most affordable and user-friendly choice for home users. The problem for 3-axis CNC machine is that it only fabricates high field surface. The surface high field direction D has to match with the Z-axis of the CNC machine. The main methodology for assembly-based CNC milling is the high field decomposition, which decomposes input shape into high field blocks. Local modification is needed for the parts whose outer surface have non-high field areas. There are 2 approaches for high field shape decomposition: the 2-step approaches and optimization approaches. Finney and their colleagues apply the 2-step approaches to first compute the base and axis of each high field block by using a polycube representation of the input shape, and then generated the geometry of blocks by performing a polycube decomposition on the shape. Montoni and their colleagues apply optimization approaches. Given an input model, they first produce a compact set of large, possibly overlapping high field blocks that jointly cover the model surface by solving an optimization. Next, a minimal set covered algorithm is used to reduce the number of decomposite blocks while allowing overlaps among them. Lastly, the overlaps are resolved by assigning the overlap portion to one of the associated blocks using a graph-based algorithm. Here ends the CNC milling. Let's move to the third part, the 2D laser cutting problems. Laser cutters can only cut 2D polygons. Despite this limitation, laser cutting has many advantages, such as high precision, high speed, and spotting a wide range of materials, making it widely used in industrial production and research prototyping. To fabricate a 3D shape, assembly-based laser cutting aims to abstract or approximate the 3D shape with a set of 2D planar parts made by laser cutting. The problems can be classified into 3 classes: spatial assembly, mesh-like assembly, and shell assembly. Joining 2D laser cut parts to form a steady assembly is a challenging task due to the limited contact area among the planar parts. The most effective way is to create integral joints on the laser cut parts, which not only stabilize the whole assembly, but also simplify the assembly process. Let's review the papers for the spatial assembly. Besides the shape abstractions, making furniture-like assemblies by using laser cut plates also gained much popularity among recent assembly works. To make stable furniture-like assembly, Schwarzberg and Pauli used the non-orthogonal half joints. The problem of this joint is that the plates can rotate around each joint. See the middle figure. So they intentionally add cycles in the assembly part graph to create non-tight but rigid joint configuration like the right figure. Then let's review the mesh-like assembly. Mesh-like assemblies are designed to abstract a free-form 3D surface with a set of ribbon-shaped slices. Signoni and their colleagues use long curved slices with prefabricated half joints, while Richter and their colleagues use short straight slices jointed with additional connectors. We take the left paper as an example. Signoni and their colleagues approximate a 3D surface with a set of curved slices that are placed driven by a smooth crossfield defined on the surface. Half joints with enlarged sleeves are constructed on the slice to enable non-orthogonal connections among the slices in a structure sound way. Lastly, let's review the papers for shell assembly. Different from spatial and mesh-like assemblies, each part in shell assemblies are oriented following the surface normal like a mesh face. The left work used additional planar connectors, while right works generate the finger joints to connect parts. Chen and their colleagues approximate a 3D mesh model with a small number of polygons that form a closed surface. By iteratively clustering mesh faces, estimating planes for each cluster, and slowly deforming the face towards each plane. Once the polygons are obtained, they are secant to form planar parts. Here comes to the last part of our assembly-based fabrication, the mixed fabrication. A straightforward idea to avoid each machine's limitation is to decomposite input shape into several sets of parts and let different machines fabricate each set, utilizing their benefits. Most of the recent works take a fast but shape-limited machine like laser cutting or prefabricated building blocks and combine it with a slow but less constrained machine like 3D printing to fabricate complex assemblies. The first application of mixed fabrication is to make large functional objects cost-effectively. Like these 3 projects try to fill the internal space of a 3D printing model with elements that are easy to make. The left paper, Gao and their colleagues used laser-cutted cuboid to make customized mouse, while the middle figures, Song and their colleagues used interlocking laser-cutted polyhedron to save printing material and time. And at the right figures, Chen and their colleagues used prefabricated universal building blocks to fill the input shape's interior, which has a better performance compared with Song's work. Another application for mixed fabrication is to make rod joint structures. Tonelli and their colleagues designed a grid shell architecture structure by optimizing a polygonal tessellation of a given 3D surface to maximize the static and aesthetic performance. Schuldambrun and Jacobson both developed their computational tools to design structurally sound road joint assemblies. The rationale behind is to dedicate complex geometry to the joints fabricated by 3D printing, while the interest strength is retained by the rods that require only laser cuts. There are more fabrication techniques that has not been discussed by our survey papers, like the molding, hot wire cutting, wire bending, and customized fabrication tool. We also see a huge potential to develop interesting assembly methods based on these new fabrication techniques. Very few of the works in assembly-based fabrication consider structural stability of the resulting assembly, as they assume fabricated parts can be connected by a wide variety of joining methods, such as glue. So this part of my talk focuses on the computational method to design structurally stable assemblies, guided by a formal stability analysis that has been described in our previous slides. We classified the structural stability problem into two classes: the assembly in equilibrium and global interlockings. To encourage disassembly, all these methods choose to use integral joints or simply planar contacts for connecting the parts. Let's first look at the equilibrium method. For volumetric assemblies, most works use the rigid block equilibrium method, which checks both forces and torques balancing conditions. For surface assemblies like the self-supporting structure, most works use the truss network analysis, which only examines the force equilibrium within the surface. Whiting and their colleagues integrated the rigid body equilibrium method with procedural modeling to design mean-3 structures that are in equilibrium under gravity. The key is to compute the derivatives of invisible energy with respect to the design parameters. They minimize the invisible energy to find physically plausible assemblies by using gradient descent. For self-supporting surface, the truss network analysis developed by Bloch and their colleagues is a well-known graphical approach. Here, G is the target compression shell and tau is the 2D projection. Tau star is the due graph of tau. Suppose that the parts' gravity loads are evenly distributed on each edge of the graph tau. A self-supporting surface is founded by adding the due graph tau star such that every polygon in that graph is closed. In addition to generating self-supporting surface, Panozzo and their colleagues also optimized the surface tessellation to avoid the resulting blocks from sliding. Note that a local geometric feature in the target shape is deformed to make the surface self-supporting. Let's move to the interlocking method. An assembly is interlocking if it can be in equilibrium under arbitrary external forces, when the key is held by other means. So interlocking assemblies has a stronger geometrical constraint than the assemblies in equilibrium. For voxelized input 3D shape, Song and their colleagues proposed a shape decomposition algorithm to construct interlocking assemblies like the left bunny. Later, they extend their method to handle smooth, non-voxelized shape for 3D printing, while the internal structure of their assembly are still voxels. The core idea of Song's interlocking method is to iteratively extract pieces while enforcing a local interlocking condition among every 3 consecutive pieces. For example, the P1, P2, and R2 is local interlocking in figure C, and P2, P3, R3 is local interlocking in figure D. Repeating this process until we find the final interlocking assemblies, see figure E. We call these assemblies the recursive interlocking assemblies. When the input is not composed of voxels but a set of parts without joints, the previous shape decomposition method would not work. For furniture design, Fu and their colleagues connected parts with orthogonal joints to make the assembly interlocking. Soon later extended their method to design interlocking polyhedrons to fill the internal space of a large 3D printing model. Their polyhedrons are assemblies of 2D laser-cut plates connected with non-orthogonal joints. Yao and their colleagues instead used the snap feed joints to construct interlocking shell models to save material and printing time. The typical approach to address these joint planning problems is to construct local interlocking groups, LIGs, which are a subset of connected parts that are locked by a specific key in the group. Once multiple LIGs as well as the blocking dependencies between them are made, the resulting assemblies are guaranteed to be global interlocking. However, the limitation of LIG-based method is that the explored space is restricted to a small subset of all possible interlocking configurations. Much larger design space can be obtained by using the directional blocking graph. Wang and their colleagues presented path blocking relations with a family of base DBGs and leveraged efficient graph analysis tools to test and compute an interlocking arrangement of the parts. Their method provided a general framework for designing interlocking assemblies, which works both on the voxelized input and the joint planning problem. In practice, equilibrium under gravity might be insufficient since the assembly could be exposed to different forces. Therefore, Wang and their colleagues further optimized the assembly's geometry such that it can be equilibrium for a cone of gravity forces. The third research topic is about reconfiguration. Reconfigurable assemblies consist of a common set of parts that can be rearranged into multiple forms for using in different situations. By reusing the component parts, reconfigurable assemblies have advantages like cost efficiency, multiple functionalities, and requiring less storage space. We classify existing works on the design of reconfigurable assemblies into two classes: free reconfigurable assemblies and hinged reconfigurable assemblies, according to whether the component parts are separable or hinged during the reconfiguration process. Let's first review recent works in free reconfiguration. For the free reconfiguration assembly, if the target shapes are provided, the problem can be formulated as geometric dissection. Otherwise, if the target shapes have been compatibly segmented, the problem is formulated as designing interchangeable parts. There is a famous theory for geometric dissection problem. That is, as long as the two 2D polygons have the same area, a dissection between them always exists. The proof does not restrict the number of parts, often leading to over-segmented parts that are physically implausible. The task of finding an exact K-piece dissection is proved to be NP-hard. Doken and their colleagues relaxed the dissection problem by letting input shapes impose soft rather than hard constraint on the dissection process, and developed a tree search algorithm to create a dissection result that approximates a given pair of 2D naturalistic shapes. Another problem is to design interchangeable parts in free reconfiguration. Given a collection of compatibly segmented 3D shapes, Doken and their colleagues partitioned them into parts and formed connecting boundaries of parts with similar segmented meaning to make these connecting boundaries identical while minimizing deviation from their original appearance. Let's then move to the work in hinged reconfiguration. Designing hinged reconfigurable assemblies requires creating not just a common set of parts, but also hinges among them. We classify the hinged reconfigurable assemblies into three classes. First, a special geometric dissection called hinged dissection. Second, the transformables that can shift across different shapes. Third, the foldable assemblies for space saving. Hinged dissection is a special class of geometric dissection that connects all the parts into a chain of hinged points and converts a shape to another by swinging the chain continuously. Zhou and their colleagues addressed approximate 3D hinged dissection problem to design an object assembly that can be folded into a box. Li and their colleagues further designed hinged dissection between two 2D polygons. Since the reversible hinged dissection does not exist for not every pair of input polygon, Li and their colleagues developed a quick filtering scheme to pick potential input shape pairs from a 2D shape collection. Their method can construct approximate dissection between two input shapes by finding a pair of conjugate chunks, which are a pair of polygons with the same edges yet in an inverse order in the two shapes respectively. The second class of hinged reconfiguration assembly is the transformables, which are physically characters whose overall shape can be changed merely by rotating or translating their components parts. Huang and their colleagues first designed transformables in virtual setup, while Yuan and their colleagues made transformables that are physically fabricable by using 3D printing. Specifically, Yuan and their colleagues first find an optimal pose of the skeleton inside the object mesh for a tight and collision-free embedding. They then use a collision-aware multiple level set-based growth method to decompose the target shape, starting from the skeleton mesh. Lastly, they find a collision-free transform between the two shapes by using a greedy search together with post-processing on the parts to remove collisions. The third problem is the hinge reconfiguration is the foldable assemblies. Given an input 3D object with a folding direction, Li and their colleagues apply a minimum amount of modification to the objects so that it can be folded to save space. Ibrahim and Yan addressed a similar problem, except that the folding direction is computed automatically rather than given. Rather than focusing on furniture, Miyamoto and their colleagues proposed a method for creating a flat foldable model with rigid panels that approximate an input 3D mesh. The fourth research topic is about tileable blocks, which are a set of geometrically unique parts whose instances can build up complex assemblies. These blocks are universal and reusable in many constructions, bringing advantages like high utilization and low cost for mass production. The most well-known tileable blocks are Lego bricks. Besides the typical problems of using Lego bricks to build assemblies, designing customized tileable blocks is also intriguing in engineering and architecture, and has recently attracted great interest in the graphic community. Let's first look at how to use Lego bricks to build interesting shapes. The most critical factor here is to make Lego assembly stable. Test 2 and their colleagues represented a Lego assembly as a part graph. The assemblies whose part graph has more edges, while with fewer weak articulation points, enjoys a better structural stability. They used a randomized greedy algorithm to search for a Lego layout by performing merging and splitting operation on the Lego bricks. Besides Test 2's work, Luo and their colleagues used force-based analysis to evaluate the stability of their Lego design. Yun and their colleagues provided a way to convert 2D pictures into a stable 3D Lego assemblies. Zhou and their colleagues fuse more Lego bricks, such as sloping or circular bricks, into their design. Their method can identify virtual features in the input 3D model and represent them with the best fitting blocks. For the customized tileable blocks, Joseph Abe discovered that identical tetrahedrons truncated at two opposite edges can be arranged to form a planar stable assembly known as Abe flat wall. Besides tetrahedrons, the cubes can also be used to create stable planar assemblies, and we name it the topological interlocking assemblies. Krishnamurti further made a connection between planar assemblies and biaxial weavings. All topological interlocking assemblies, once their boundary blocks are fixed, are proved to be in very good mechanical properties, such as high strength and toughness by physical experiment. The above-mentioned tileable blocks are designed for constructing planar assemblies, although these 2D methods can be adapted to create 3D topological interlocking assemblies. These blocks will not have identical shape anymore, as their geometry has to be modified to follow the curvature of the surface. This limitation motivates research to design tileable blocks for building 3D shapes, like the SL blocks at the left and the interlocking voxels at the right, which can approximate general 3D shape. John and their colleagues designed a set of 9 tileable blocks with integral joints called the interlocking voxels. By using a hierarchical and layer-by-layer assembly order, these blocks can build up voxelization like assemblies that globally interlocking. Now we move to classification and discussion. We made this table at the left to summarize the relation between papers, and we found that same method can be applied to different fields. For example, the high field decomposition done by Montoni and their colleagues, and the pyramidal decomposition paper done by Wu and their colleagues both use the set-covered algorithm. This table also provides potential future works. For example, the equilibrium problem is solved by shape decomposition and part optimization. Could we solve this problem by using joint planning and layout optimization? Note that not every combination between design objectives and problem formulation will make sense. For example, designing structural stable assembly is not suitable to be formulated as a shape code decomposition problem, since this assembly typically have a single geometric form. So here are some future works. To simplify computational assembly of a design, a common assumption is that the fabrication material is rigid and the manufacturing precision is perfect. Yet in practice, materials are not infinitely rigid, and the fabrication devices have limited manufacturing precision. As a consequence, structural issues can arise when the relative motion of 2 parts is restricted by a small contact or a thin joint. Internal stress concentrations at the contact or joint can lead to material failure. Similarly, a geometrical stable design could become unstable when fabricated due to gaps among the parts caused by machining tolerances. To improve prediction accuracy, one possible way is to take these imperfections into consideration in the analyze methods. The contact finite element analyze and tolerance analyze are 2 mature forward simulations that are widely used in mechanical engineering. Design assemblies that are robust for these imperfections would be an interesting inverse problem. We have discussed a number of objectives for designing assemblies. To date, however, most publications address and solve a specific objective and do not consider all aspects relevant for assembly. For example, for large-scale assemblies in architecture, combining the objectives of parts fabricability, structure stability of the final and intermediate assemblies, and automated assembly process planning would provide a more complete framework for design. Advanced design method can be studied by exploring several aspects of assemblies in a novel way. First, existing design method connects parts by using either integral joints that allow a single part remote direction or planar contact that have limited capacity to restrict part motion. Study integral joints in between these 2 extremes, as well as how they facilitate design assemblies, would be an interesting topic for future exploration. Second, design assemblies with assembly plans that are beyond sequential, momentum, or linear is another promising research topic, as these complex plans are possible to be precisely realizable by robots nowadays. For example, the left triangle can be disassembled by moving the bottom 2 parts downwards simultaneously. The right cube can be disassembled by using both translational and rotational motions. Such assembly plans could be useful in terms of entertaining people or enhancing structure stability. In recent years, tremendous research efforts have been developed to solve traditional graphics problems such as shape synthesis and mesh segmentation using machine learning methods. However, for assembly problem, there are less works using machine learning. But could we try some? For example, finding the optimal assembling sequence for assemblies to reduce scaffold is an interesting but very difficult task. Applying the reinforcement learning where we regard each assembly step as an action to solve the difficult assembling planning problem could be a promising future work. That's this to the end of our talks. Thank you for your listening.